Welcome to the problem solving session for the week 3 on the topic Abstractions from Precipitation for the NPTEL course Surface Water Hydrology being taken by Professor Dr. Rajiv Maiti from the Department of Civil Engineering IIT Kharagpur. I am the teaching assistant Aman Srivastava, and today we will be solving some focused numerical problems on this topic such that the enrolled candidates could solve the weekly assignment on the NPTEL. So let's move ahead. Today in this problem solving session, we will be focusing on three aspects for the topic abstractions from precipitation, namely evaporation process, evapotranspiration process, and infiltration process. So let's start with the infiltration process. Here is the first problem for today's class. Here is the problem. A canal of length 50 km has an average surface width of 10 meter. The mean daily evaporation measured by class A pan in June is 2 cm per day. Estimate the total amount of water evaporated from the canal in June. Assume the pan coefficient as 0.85. Okay, so we are provided with the length of the canal, which is 50 km. The width of the canal is also given, that is 10 meter. So we can utilize these two inputs to find out the area of the canal. Likewise, they have also provided the type of pan that was used to measure the daily evaporation, that is class A pan. And the rate of evaporation is also mentioned, that is 2 cm per day. So the problem is asking us to estimate the total amount of water evaporated from the canal in June. So when it is mentioned total amount, it is basically indicating towards the volume of the water evaporated from the canal in the month of June. So June here indicates that there were 30 days in that month for which the entire measurements were taken. And the pan coefficient is also provided, which is 0.85. Okay, so utilizing these inputs, let's see how to take approach to solve these kinds of problem. So step 1 will be to find out mean daily evaporation in centimeter per day. Okay, so how to find out mean daily evaporation? We need to simply multiply the pan coefficient, which is provided in the problem, with the pan evaporation rate, which is also provided in the problem. So substituting both of them from the problem, which was 0.85, that is pan coefficient, and 2 cm per day was the pan evaporation. So by multiplying, we get 1.7 cm per day as the mean daily evaporation. In the step 2, we need to now find out the mean monthly evaporation depth in meters. So in the step 1, our focus was on rate of evaporation, but in the step 2, our focus is on finding the depth of evaporation, that too at the monthly scale. So how to solve such measures? Here the mean monthly evaporation depth can be estimated by multiplying mean daily evaporation, okay, so that we have already estimated in step 1, and multiplying it with the number of days in the month of April. Okay, this is wrongly written, it should be June. So the number of days in April or June is 30, so multiplying that with 30 will give us the mean monthly evaporation depth of 0.51 meter. So this is what we have identified in step 2. So taking our calculations forward, in the step 3, we need to find out the area of the canal in square meter. And we know that both the length and width is provided in the problem, which is 50,000 meter. Initially in the problem, it was given in 50 in the units of kilometer. So 50 kilometers is nothing but 50,000 meter, and that is measured with the width of the canal, which is 10 meter, and we get 5 lakh meter square as the area of canal. And in the step 4, we need to find out now the mean evaporation volume, which is what is actually asked in the problem in the units of meter cube. So how to find out that? Here mean evaporation volume can be estimated by multiplying area of canal, okay, that is meter square, with the mean monthly evaporation depth, which was meter. So we have estimated this in the previous step, that is step number 2 in the previous slide, which was 0.51 meter, and here the area of canal, which is just now we have obtained, which is 5 lakh meter square. So multiplying both of them, we get 2,55,000 meter cube of the volume which actually evaporated. It is that volume of water which got evaporated in the month of June in the units of meter cube. So this is how we have identified the response to the problem which is given. So we can actually reduce the final response as 2.55 into 10 power 5 meter cube, and this is the final response of the question. Okay, so let's move ahead and solve another problem on evaporation process. Let me read the problem. The following climatic data were collected at a reservoir for the month of September. Mean monthly temperature was obtained as 35 degrees Celsius. Net radiation of evaporable water, that is HN, was 10 mm per day. Psychrometric constant was obtained as 0.5 mm of mercury, Hg, per degree Celsius. Actual evaporation was obtained as 12 mm per day. Evaporation of the slope of the saturation vapor pressure versus temperature curve at the mean air temperature, which is indicated by A, is 2 millimeter of mercury per degree Celsius. So using the Penman formula, calculate the evaporation in September by assuming that the lake evaporation is same as potential evapotranspiration. Okay, so keeping this consideration in mind, let's utilize all this data and find out the evaporation in the month of September. Okay, so in the step 1, we need to first of all find out the daily potential evapotranspiration in mm per day. So this is the rate that we need to find out for PET. So here is the formula. Okay, so PET is expressed as AHN plus EA gamma by A plus gamma. Here this gamma is nothing but its psychrometric constant. A we have already seen in the previous slide. It is slope of the saturation vapor pressure versus temperature curve at the mean air temperature. And we have also seen what is HN. It is net radiation of evaporable water. And what is EA? It is the actual evaporation. So substituting all those values which were provided in the problem, we get PET as 10.4 mm per day. I hope you were able to follow this discussion. Now the step 2, we need to find out the monthly lake evaporation depths in meters. Okay, this is slight change. It should be meter. I have written here as centimeter. Okay, so how to find out that? First of all, we know that PET is 10.4 mm per day that we have seen in the previous slide. Okay, so now the month is September, so there are 30 days in the September. So the way to find out the depth, just we have seen in the previous problem as well, is to multiply this rate with the number of days in that particular month, and that's why we get the PET, which is equal to E, which is also given in the problem, that the potential evapotranspiration should be treated as the evaporation depth. So 10.4 mm per day is multiplied with the number of days 30, and finally it has been converted into into centimeter instead of meters. Okay, so finally we have obtained evaporation as 31.2 centimeter, and this is what is the response that we actually wanted to determine for this problem. I hope you were able to follow this problem, although so many data were provided, but the steps were very focused and very apparent to arrive at the depth of evaporation. Okay, now let's move towards the third problem for this live interactive session. It is on the evapotranspiration process. So let me read the problem. The net radiation from an open water source is 343 watt per meter square and the air temperature is 14 degrees Celsius. Estimate the evaporation rate in mm per day. Assuming that the sensible heat, ground heat flux, heat stored in the water body and advected energy are zero. The density of water can be assumed as 1000 kg per meter cube for the present condition. Okay, so here we need to find out evaporation rate, or more specifically when we will look into the equation, then we will get to know that we are required to find out the evapotranspiration rate in mm per day, and for these conditions which are provided here. So net radiation is given as 343 watt per meter square, air temperature as 14 degrees Celsius, and also there were certain other energies like sensible heat, ground heat flux, heat stored in the water body and advected energy. They all are considered zero, and the density of water as usual is assumed as 1000 kg per meter cube for the given air temperature. So now let's utilize this information and find out in the step 1 the latent heat of vaporization. So how to find out this L, that is latent heat of vaporization for temperature 40 degrees Celsius? Here is the equation. L is equal to 2501 minus 2.37 T. So here T is 14 degrees Celsius. Let's substitute and obtain the latent heat of vaporization in the units of joule per kg as 24,67,820. So this is how we have obtained the latent heat of vaporization. In the step 2, we need to find out the energy balance for an evaporative surface. Okay, so this is the equation for the energy balance. Hn is equal to Ha plus He plus Hg plus Hs plus Hi. All these information are provided in the problem. For example, we see here, this is the sensible heat Hs, ground heat flux Hg, heat stored in the water body, and advected energy, that is Hg. So these all variables are provided in the problem. But the fact is, like, Ha is 0, Hg is 0, Hs is 0, and Hi is also 0. So altogether we are left with He. So the Hn is equal to He based on the conditions provided in the problem. Okay, in the step 3, we need to find out the evaporation rate in mm per day. So Hn is equal to He is equal to rho L El. Okay, so this is the formula to be utilized in the step 3. And now all this information is now with us. We know the density of the water. We also know the latent heat of precipitation L. And now we have to utilize this information to find out the EL, that is evaporation rate in mm per day. Okay, so we can rearrange the above equation as EL is equal to Hn upon rho L. Now we know what is Hn, that is provided in the problem, 343 watt per meter square. We know rho, that is 1000 kg per meter cube, and we also know L, which is 24 lakh 67,820 joule per kg. So if we solve this equation and also take into account the units, finally we will get 1.389 into 10 power 7 meter per second as the rate of evaporation. But we are supposed to find out the evaporation in mm per day. So let's convert this meter per second into mm per day, and here is the conversion. This is how we have converted, and finally we have obtained 12 mm per day as the final response to the conditions provided in the question. So this is 12 mm per day is the final evaporation rate for the given condition. I hope you were able to follow this discussion, and let's come to the last part of today's live interactive session. Let's solve question number 4 on infiltration process. Here is the problem. The mass curve of a single storm in a watershed of area 1000 hectare is as follows. So time from start, that is 0, 2, 4, 6, 8 hours, and corresponding to each of these hours, the cumulative rainfall depth is provided, that is 0, 0.6, 2.4, 3.6, 4.2 centimeter. So direct runoff produced by the storm at the watershed outlet is 0.25 million meter cube. So volume of the direct runoff is provided, and we are required to estimate the phi index of the storm. So let's see, utilizing this information, how we can find out the phi index of the storm. So here is a step 1. First of all, let's find out the runoff depth in centimeter. Okay, so volume of was provided. So how to find out the runoff depth? This will be that what was the total direct runoff volume which was provided in the problem, and watershed area which was also provided in the problem. Substituting these values as given in the problem, we substituted and converted it into centimeter, and finally we get 2.5 centimeter as the runoff depth. Now in the step 2, now let's find out the rainfall intensities corresponding to each time period which is provided. Here we can see that the time period we have 0, 2, 4, 6, 8 hours from the beginning, and the time interval will be definitely delta t is equal to 2 hours. So it is like 2 minus 0 or 4 minus 2, 6 minus 4, 8 minus 6. So altogether we are getting 2 hours interval corresponding to each observation. So let's consider each observation as pulse. So we are having 4 pulse, and this is the time from the start of the rainfall to 4, 6, 8 in the unit of hours, and this is the cumulative rainfall depth which was provided in the problem. Until here it was the problem. Now let's find out incremental rainfall. So how to find out incremental rainfall? Let's focus on this two components, 0.6 and 2.4. Okay, so if I want to find out incremental rainfall, here this was the first observation, so that's why we have taken 0.6 as it's. But in order to get the incremental rainfall at the second pulse, what we have to do is just subtract both of them, 2.4 minus 0.6, and that will yield 1.8. Okay, so this is how we have obtained the incremental rainfall against each pulse. Now in the next step we need to find out the intensity of rainfall. So how to get it? This is in the unit of centimeter per hour. Here we are having 2 hours. Okay, so the time interval 2 hours is provided to us. So 0.6 divided by 2 hours will give you 0.3 centimeter per hour as the intensity in the pulse number 1. Likewise, 1.8 divided by 2 hours will give you 0.9 centimeter per hour. And likewise, for the fourth pulse, it was 0.6. So dividing this 0.6 incremental rainfall depth by the total number of hours or time interval, that is 2 hours, it will yield 0.3 centimeter per hour. I hope you were able to follow this table. Now let's utilize the intensity of rainfall in the next step. So from here, I want your full attention. In the step 3, we need to select m number of pulses in decreasing order of rainfall intensity. And here, let's first of all take m equal to 4. So this is how we are randomly starting. Okay, so there were 4 number of pulses. So I have assumed m equal to 4, and this is equal to the number of pulses, that is n equal to 4. So n here is the number of pulse, and m is what we are actually taking the number of pulses in decreasing order of rainfall intensity. Okay, and we all also know that the time interval delta t is 2 hours. So let's use this time interval to find out the effective time for the given time interval. So how to find out effective time? Effective time TE is expressed as m into delta t. So here m we have taken as 4 and delta t is the time interval, which is 2 hours. Substituting these values, we will get effective time as 8 hours. Okay, now here in this case, in this trial number 1, m is equal to n, that is the number of pulses that we have selected is equal to the total number of pulses, that is n equal to 4. Hence, runoff can be expressed using this formula where RD, that is the depth of the runoff, is equal to, it is a summation from I equal to 1 to 4, because there are 4 pulses only, and we have also considered m as 4. And this is the intensity of rainfall minus phi, which is the phi index, into delta t. This is what is the equation to be utilized to express runoff depth. Okay, so this is what now we will be utilizing in step 4. And this was the intensity of the rainfall I, which we obtained in the table in the previous slides. So these are the final rainfall intensity values that we have obtained for each of the pulses. Okay, so let me rearrange this equation. So here I is multiplied with delta t minus phi index is multiplied with delta t. Okay, another aspect is, since we are considering I from 1 to 4, here we are having 4 into delta t as the effective time. I hope you were able to follow this step also. And we are multiplying it with 4 because there are 4, m is equal to 4. Okay, so all the 4 pulses are taken into account in the trial number 1. Okay, so now let's substitute the values inside it. So I into delta t. So here 0.3 plus 0.9, 0.6 plus 0.3. These are the intensity of rainfall. All together they are multiplied with time interval, which is delta t, that is 2 hours. Okay, and minus phi, that is what is unknown that we need to find out, into 4 into delta t. Delta t is nothing but 2 hours. Okay, and we already had calculated in the step 1 what was the depth of the runoff, which is 2.5 centimeter. Okay, so now let's solve this equation to find phi. And if you solve this equation, you will get phi as 0.2125 centimeter per hour. Okay, so this is considered as the final answer. Why? Because you see this phi value is smaller than all these values which are provided here. Okay, so there is no need of conducting trial number 2, because the phi that we obtained here is 0.2125 centimeter per hour, which is the lowest value among all these values. Okay, so here MC, which is the number of pulses having II greater than equal to phi, is 4, and this 4 is equal to the number of pulses that we have to select, that we selected, that is m is equal to 4. So both these values are matching, that's why there is no need of further iteration, and trial 1 provided the final response, that is phi is equal to 0.2125. So I hope all the enrolled candidates who are watching this video must have followed how to solve problem on infiltration process. So today in this lecture, we actually focused on these 3 aspects of the abstractions from precipitation, respectively evaporation process, evapotranspiration process, and infiltration process. So I hope you were able to understand all these problems, and I'm pretty sure these numerical problems will help you to solve the weekly assignment which is being released from the NPTEL portal. So stay tuned for more such problems in the week 4. Till then, thank you and stay connected.